Hello, welcome to this problem solving session in physics. In this session today, we are going to solve problems on the topic Doppler effect. As you know, the Doppler effect is a very important topic from JEE Advanced uh, point of view because each year at least one question, or almost each year at least one question is always asked on Doppler effect. I am sure all of you know what is a Doppler effect. It is our everyday experience that the pitch or the frequency of the whistle of a fast moving car seems to drop down as it passes us. This is basically the phenomenon of Doppler effect. Let us work out some of the formulas that you will need to solve problems based on Doppler effect. The idea is that you need not have to memorize any of the formula. You can work it out from the very first principle, because generally it is seen that students tend to memorize this formula without understanding it, and therefore they end up in making a lot of mistakes. So let us work out these formulas. First, let us consider the case where the observer is at rest and source moving towards the observer. Okay, let us analyze this case first, where this is my source of sound, and this source of sound is moving with some velocity u, capital U, towards the observer, and observer is at rest. So this is my observer and this is source, and this source has frequency of the sound. The source is nu, and our objective is to find the frequency as measured by the observer. Okay, so to do that, let us rely on the basic formula for the frequency. You know, the frequency is velocity divided by wavelength, right? So this is the only formula that just you need to remember to work out everything. So that's why I said you can work it out from the fundamental or the first principle. So frequency as measured by the observer would be frequency of the sound. That would be here velocity of sound as measured by observer, and it would be divided by the wavelength of sound. Okay, first let us find out the wavelength of sound as measured by the observer. So you know, first of all, in the case of sound wave, the wavelength is basically the distance between successive crest. Okay, so first let me work out the wavelength. So this is the source of sound, and a pulse is suppose released by the source at time t0, and then it will travel this much of distance. So u is the speed of sound, so the distance traveled by this crest would be this much, and the next crest in the meantime this source would travel by, say, this distance ut0, because so this much of distance would be traveled by the source, because capital U is the velocity of the source. So now if I look at the successive distance between the crest, then that, let me term it as L. L is the wavelength or distance between successive crest. That would be, from the figure it is very clear that would be simply ut0 minus capital U t0. So therefore it is u is the small u is the speed of sound, capital U is the velocity of the source. It will be multiplied by t0. So the frequency as measured by the observer is at rest. So it is, first of all, the velocity of sound as measured by the observer is obviously going to be the same as that of the sound with respect to air or the stationary medium, because observer is stationary. So it is u, and then wavelength is u minus u0, u capital U t0, and you know that 1 by t0, that is nothing but the frequency of the source. So therefore I can write nu is equal to nu into u small u divided by small u minus capital U, and capital U is the velocity of the source. So this is the formula I get. So similarly, we will be able to get the formula for, say, the source. Say the source is moving away from the observer. It is, say, moving away from the observer with velocity u, and the observer is at rest. So this is observer, and this is the source. So in this case, only a difference would be that speed of sound as measured by the observer would be simply u, okay, or velocity of the sound as measured by the observer would be u, because observer is at rest. But the wavelength of sound as measured by the observer, that is going to change because the source is moving away, right? So okay, let me just explain it quickly. So in time t0, the crest, one crest would be, this would be the distance, so this is ut0, and in the meantime the source would move towards this distance, so this would be, say, capital U t0. So therefore you see the total distance or successive distance between crest would be u plus capital U t0, and therefore here you have to write this is the wavelength in the denominator. It would be this. So the formula would, then you can write it as nu u plus capital U, and quite clearly, as you know from intuitively also, as the source is moving away from the observer, the frequency should actually reduce, and that's why you see in the denominator you get a bigger number compared to the numerator. So the frequency as measured by the observer would be less than the source frequency. Okay, so now you can combine both the cases here. So you can write a combined formula when the observer is at rest but the source is moving. Then you can write the whole thing as u plus minus, say, capital U. Just for remembrance purpose, you can put a suffix s here. Thereby I mean that I'm talking about the source. Here plus refers to the case when the source is moving away from the observer, and minus refers to the case where the source is actually moving towards the observer. Alright, so this is how we can work out all the other cases also. Now in the next case, what we can consider is that, say, source is at rest and observer moving towards the source. So same physics again. So you have this source. Now the source is at rest, so u is equal to 0. So this is my source and this is my observer. Now observer is moving towards the source with velocity, say, capital U. Now in this case, again, as regards the wavelength is concerned, you see, it would be exactly the same. It would be okay, let me just explain it. Because the source is at rest, I think, because the source is at rest, just a minute. Okay, let me do it here. As regards the wavelength, the source is at rest, so therefore at time t0 this crest has moved this much, and this is ut0. But because it is at rest, so again the next crest is also going to emanate from it. So the distance between successive crest is simply going to be ut0. Okay, so L is simply ut0, wavelength. What about the velocity? Okay, the formula would be velocity as measured by the observer. Because velocity of sound as measured by the observer, sound velocity is u, with respect to u is the velocity of sound with respect to the stationary medium, that is air, say. And now with respect to stationary medium, this observer is moving towards this source, so it is u minus u, because sound velocity is along this direction and it is in the opposite direction, so you have this. And then wavelength is ut0, so immediately you get this formula, u plus capital U divided by ut0, right? And which I can write in a more simplified form as nu into u plus capital U divided by u. So this is the formula you get when the this observer, actually let me use a different symbol for observer. I think I use capital V, so let me use capital V here, so that all right, so let me use capital V, let me write, and here also capital V. Okay, so I have here, it would be capital V. Okay, so this is the formula I get. Now I think you can immediately see if the source is now at rest, but the observer source is at rest, so this is your source is u is equal to 0, and the observer is moving away from the source with velocity capital V. Then the formula that you will get is, this is observer, it would be nu dash is equal to nu u capital U minus V, and that is obviously should be the case, because as the observer is moving away from the stationary source, the frequency should actually, as measured by the observer, should decrease. So in this way, now I can work out another formula, say where both source and observer are moving. Let us analyze this interesting case, where suppose the source is moving towards the observer. Suppose both of them are moving towards each other. The source is moving with velocity capital U and the observer is moving with velocity, say, capital V. And now our goal is to find out what is the frequency as measured by the observer. So this is our observer and this is our source. So let us again, it would be nu dash would be frequency as measured by the observer would be velocity of sound as measured by observer, and then wavelength of sound. Okay, so velocity of sound as measured by the observer, as you can see from the diagram, if you just look at it, so velocity of sound with respect to air is u, but the observer is moving towards it, so velocity as observed velocity of sound as observed by the observer would be u minus capital V, right? So, and what about the wavelength of sound? Wavelength of sound would be, that is the distance between successive crest, because this already we have analyzed, because the source is moving towards the uh, towards the observer. It would be u, the distance between successive crest would be u minus capital U t0, and therefore I can write down the formula here, that would be nu into nu small u plus capital V divided by small u minus capital U. Here this capital V is the velocity of the observer and capital U is the velocity of the source. So in this case, in this formula, what is happening is that both the observer and the sound are moving towards each other, and if you see that the denominator numerator is increasing, denominator is decreasing, thereby enhancing the observed frequency, which is also physically speaking has to be the case. So I think I have given you the message loud and clear here, that how you can work out various formulas, and you can actually now analyze the formula for, say, when the source, I can actually work it out, say source and observer, say source is or say both of them. Now I have here here both source and observer moving towards each other, okay. And now in the we can also consider both source and observer moving away from each other. So this also you can work out if you have understood whatever I have explained. So it would turn out to be nu dash, the frequency as observed by the, as measured by the observer, would be frequency of the source into, this would be velocity of sound, u minus velocity of the here it would be the observer, and this would be u plus the velocity of the source, okay. So this is what you are going to get, and you see effectively the frequency of sound as measured by the observer is now going to reduce, and both this is reinforced by numerator and denominator. Numerator is decreasing, denominator is increasing, thereby overall this frequency as measured by the observer is also going to decrease, okay. So now as we have learned how to derive these formulas for various cases, so let us work out some problems. Okay, let us work out this problem. This was asked in 2011 JEE Advanced. So the problem goes like this: a police car with a siren of frequency 8 kilohertz is moving with uniform velocity 36 km per hour towards a tall building which reflects the sound waves. The speed of sound in air is 320 meter per second. The frequency of the siren heard by the car driver is. So you are asked to find out the frequency of the siren heard by the car driver where the this car is actually moving. So the situation is actually like this. Say this is my car. This car is moving with some velocity u is equal to 36 kilometer per hour, and you can immediately see that this is actually nothing but 10 meter per second. So the car is moving with speed 10 meter per second, and it is moving towards a standing wall here, okay, a tall building. Suppose this is the tall building, and this building is reflecting sound waves. All right, so what we have to find out is that what is the frequency that is heard by, as this, this car is moving uh, towards this building here, towards this building. So what is the frequency that is heard by this car driver in the car? And originally the frequency of this, anyway, the siren frequency is 8 kilohertz. Okay, it is given to be 8 kilohertz. So it's a simple problem, a little bit technique you have to apply. Whatever I have taught you about the formula, the way we derived it, you can apply those knowledge here. Let us do it. So first of all, let us see, suppose somebody is in this building, how the observer in a building is going to measure the frequency. So let us say the new one is the frequency measured by an observer which is at rest, basically, because it's situated in the building. Observer in the building. Okay, so let us work it out. Nu 1, the source is moving towards the observer, so source frequency is nu s, that is the siren frequency. Now velocity of the sound with respect to the building, because the observer is at rest, so therefore it is simply u. All right, that is the sound, that is as it is given to be 320 meter per second, and the wavelength of sound as observed by the observer in the building. So because this, as we have discussed already, that as this source is moving towards it, so therefore the wavelength would be u minus capital U into T0, which is already incorporated here, that is the signal siren frequency. So this is the formula we have to apply. So let me just put down the number here. This is 8 kilohertz, right? So this is 8 kilohertz, and then this is 320 meter per second, and this is 320, and this is 10, so this would be 310. So this much of kilohertz is the frequency as measured by the building. And because this is again reflected back, now you see the reflected sound wave, it is now going to act like a source. So, and this would be now our observer. So therefore now the source is at rest and observer is moving. So let us say nu dash is the frequency as measured by the observer. Okay, so our source frequency is here nu 1, and velocity of the sound as measured by this driver in the car, because what is happening is that the car is moving towards the observer now. So the velocity would be of sound as measured by, this would be u plus capital U, right? I think that is easy to understand, because this is moving with velocity capital U and sound is coming towards this direction, right? So therefore this is what you are going to have. And as regards the wavelength, that is this is now acting as a source, so it would be u, wavelength would be u into T0, but T0 is already would be nu 1 by T0, so therefore it would be simply this. So this is the formula we have to apply. Now I have nu 1 with me, so nu 1 is, let me write, 8 into 320 divided by 310 into, this is 320, and then this would be simply 330. So you have to just work out 8 into 33 divided by 31. So if you do the calculation, it would turn out to be around 8.5 kilohertz. So this should be the answer, and this is going to be the frequency of the siren heard by the car driver. So correct option is A. Okay, let us solve this problem. This was asked in the year 2003 JE. A police car moving at 22 meter per second sounds a horn at 176 Hz while chasing a motorcyclist. Both police car and motorcyclist are moving towards a stationary siren of frequency 165 Hz. What is the speed of motorcycle if it is given that the motorcycle cyclist does not observe beats? Alright, so we have to basically consider this motorcyclist as the observer here. Okay, let me write here, this is our observer, and we have two sources. Now this is the police car, this is source number 1 S1. It is moving towards the motorcyclist, and the motorcyclist is moving away from the source police car with velocity v. And then we have also a stationary source, so let us say that is S2, and this is at rest. So this is, say, capital V is equal to 0 here. First, let us work out the frequency as observed by the motorcyclist when I take S1 as my source. Okay, so nu1 is the frequency, this is the frequency observed, or rather I should say measured, whatever, frequency measured by motorcyclist when S1 is taken as the source. Okay, so let us work it out. So nu1 would be this police car, it's horn at 176 hertz. So this is a nu, so let me say nu p, that is the police car here, the frequency of the car, or the whistle in the car, whistle in that car. Then you have, alright, so velocity of the sound as measured by this observer would be, because it is moving away from the source, so with velocity small v, speed of sound is, velocity of sound is u, and this is moving away, so velocity of sound would be u minus, it would be u minus v, right? So this is what you will have. And then what would be the wavelength? Wavelength would be, this is the source is moving towards the observer with velocity capital U. So as I explained in the theory section, we have to have U minus capital U, okay, into T0, but 1 by T0 is this frequency, right? So therefore this is the formula you have to apply. So let us just write it down here. So what we are having, nu p is given to be 176 hertz, right? You just see this diagram here, 176 hertz, u is 330. You have to actually find out the speed of the motorcycle. We don't know its speed, we have to work it out. And this is 330 minus capital U is here given to be 22. Okay, this is one thing we have. And another one is nu2, because you see in the problem what is asked is what is the beat. So therefore we have to calculate the frequency observed by this observer, this motorcyclist, from the source S1 as well as from the source S2. So frequency from the source S2, that is nu2, that would be, now this stationary source is say nu s, that is, what is this frequency, that is given to be 165 hertz, right? Okay, I will write it later. First of all, let us write down the formula. So because this source is now at rest, so uh, and the observer is moving towards the source, so therefore the velocity of sound as measured by this observer, okay, that is the sound that is coming from this source S2, is obviously be u plus small v, okay. And the wavelength of sound would be, because this source is stationary, that would be simply u into t0, but this is already taken into account. 1 by t0 in this case is the source frequency. So this is what you have to use. So this is 165, nu s is 165, and then you have 330 plus v, this is what you have to work out, and u is 330. Now what is beat? Beat is basically difference in the frequency. So nu1 minus nu2 is the beat frequency. What is asked is that what should be the speed of the motorcycle, okay, if it is given that the motorcyclist does not observe beats, that means nu1 minus nu2 should be equal to 0. So therefore if I equate, say let us say this is my equation number 1 and this is my equation number 2, then I can get this set of equations. Just let me write here. That would be 176 divided by 308 into 330 minus v, and this is equal to 165 332. This is immediately we see this is 1/2 into 330 plus v. Okay, this is very easy to solve, because if you just see this would turn out to be 4 divided by 7, and if you work out this, then this should simply turn out to be 330 by 15, and this would be 22 meter per second. So therefore the correct answer here would be this option number B. Okay, so that's the answer. Now let us work out this problem that was asked in 2002. A siren placed at a railway platform is emitting sound of frequency 5 kilohertz. A passenger sitting in a moving train A records a frequency of 5.5 kilohertz while the train approaches the siren. During his return journey in a different train B, he records a frequency of 6.0 kilohertz while approaching the same siren. The ratio of the velocity of train B to that of train A is. So we have to find out the correct option. So let us do it. First of all, let us see, let us just understand it pictorially. So what is happening is, say this is my train A is approaching this platform here. Say this is the platform, and in this platform this siren has emitting sound at frequency 5 kilohertz. Okay, and then again in the second case, what is happening is that during his return journey in a different train B, he records a frequency of 6 kilohertz while approaching the same siren. So let us say again we have this is, it is a different train B. If it approaches this platform, and he is going to see a different frequency, say nu B here, and here when it approaches this platform in the train A, it see this frequency nu A. All right, and let us work it out. We have to find out the velocity or is not given, both train A and B. So let us, we have to basically work that out. So first of all, my nu A, the frequency of sound as measured by train A would be, this is the platform the siren frequency at the platform, which is our source is at rest here. So velocity here, now velocity of sound as measured by this observer at train A, that would be, or passenger at A would be u
minus, say this is, say with it is approaching with velocity, say v1, capital V1, so it would be v1. And right, and then because the source is at rest, so therefore it would be simply u, that wavelength would be u t0, right, and there 1 by t0 is new already, so we have this. So this is one expression we have. If I just write the put the values here, that is 5.5 kilohertz, right. If you see, it trade a records a frequency of 5.5 kilohertz. So, and this is your 5 kilohertz here. This is the source frequency is 5 kilohertz. So I have u minus v1, or I can simply write 5 minus 5 v1 divided by u. So this is my equation number, say 1. Or I can also write it as, if I just take simplify this further, I will get, it would be half minus 5 v1 by u. Okay, so let us say this is, okay, this is equation number 2. In the second case, now the frequency measured by the passenger at train B, again it is approaching the same siren, so the same formula is going to be applicable here. That would be u minus v2 divided by u. So now if you put down the numerical values, this is, I have 6 kilohertz and this is 5 kilohertz. Then this is u minus vt, and then I have 5 minus 5 v2 by u. Okay, then this can be further simplified as 1 is equal to minus 5 v2 by u. So this is my equation number 3. If I take a ratio of equation 3 and 2, if I divide 3 by 2, then I will be able to get the ratio between the velocity of train B and train A. So v2 by v1 would be simply equal to 2. A very simple straightforward problem. So correct option would be, in this case, would be option number B. Let us now consider this problem. This problem is a little bit off track because it is not directly related to sound wave. The problem goes like this. In hydrogen spectrum, the wavelength of H alpha line is 656 nanometer, whereas in the spectrum of a distant galaxy, H alpha line wavelength is 706 nanometer. Estimated speed of galaxy with respect to Earth is. So you are asked to estimate the speed of the galaxy with respect to Earth. This problem can be used by the principles that we have learned. So let us do this problem. This was asked in 1999 JEE. So here I can consider this galaxy as my source. So this is my source and Earth is my observer. Earth is an observer, and observer standing at Earth is making measurement of the light that is coming out of the galaxy. And this galaxy, because you see the wavelength here is on the higher side, so obviously the galaxy should go away from the is moving away from the Earth. Suppose it is moving away from the Earth with speed u. So this is basically the setup we have, and the speed of light is, say, c. Now let us work it out. The frequency as measured by the Earth, that is emanating from this galaxy, is, say, nu dash, and that we can work it out by this formula. That would be velocity of light as measured by Earth observer, and then that would be divided by wavelength of light measured by Earth observer. Okay, this simple formula is good enough. Now you see velocity of light as measured by the Earth observer would be, because the Earth is the observer and this is at rest, so it would be simply c, speed of light. And on the other hand, the wavelength of light, okay, let us just quickly get that would also be in the similar way that we have worked out earlier. So suppose this galaxy is here, so it is emanating a signal. So at time t0, this has gone by a distance, this is c t0, and in the meantime the galaxy would travel a distance, say c u, sorry, it would be uh, capital U t0, right? So now then we can say the distance between the successive crest would be c plus u into t0, and 1 by t0 is the frequency, so therefore I have the formula would be c plus u, and then this would be nu. Now again, you know that wavelength is lambda, wavelength is c divided by the frequency. So from here I can write this particular formula here. This formula I can write as simply in terms of wavelength as okay, let me just quickly work it out. You can immediately see that I'll be able to write it as 1 by lambda dash is equal to 1 by lambda c plus capital U. So this is the formula that we can now use. Now everything is given to us. Lambda dash is given, that is 706 nanometer, and lambda is given to be 656 nanometer. I'm just taking it this side, and then I have c divided by c plus capital U. Now if you just do it quickly, you will find that this would be simply 0.93, and then if I take this side, so it would be c plus 0.93 u, and that would be equal to c. And from here you can find that u would be equal to, if you take this side, all right, then you will get 0.07 divided by 0.93 into c. So if you work it out, then it is going to give you 2.3 into 10 to the power 7 meter per second, where I am taking c is equal to 3 into 10 to the power 8 meter per second. So therefore the correct option here would be option B. Okay, so this is the correct answer. This is a little bit off the track, but you see that by using the from first principle you can anyway work it out, this problem also. Okay, let us now work out this very interesting problem from 2016 JEE Advanced. This problem, it will take a bit of time to read it, so let me explain it from the very beginning. So it says two loudspeakers M and N are located 20 meter apart and emit sounds at frequency 118 Hz and 121 Hz respectively. A car is initially at point P 1800 meter away from the midpoint Q of the line MN and moves towards Q constantly at 60 km per hour along the perpendicular bisector of MN. It crosses Q and eventually reaches point R 1800 meter away from Q. Okay, let us understand the situation, what's going on here. So we have two loudspeakers situated at M and at say N, and their distance is given to be 20 meter, and a car initially at point P 1800 meter away from the midpoint of Q. So this is the situation. So it is it is not proportional, but okay, you can take it to be, it is say situated around 1800 meter away from the point Q, and as it crosses Q, and then it ultimately reaches the other end of the point, that is at R, which is also 1800 meter from the point Q. So basically P and R are symmetrically located from the point Q. Okay, now given that nu t represent the beat frequency measured by a person sitting in the car at time t. So the car is actually starting from here, it's moving with some velocity, say capital U, okay, along this direction, it's moving, and we have to actually, what is asked here, that the beat frequency you are asked to find out. Let nu p, nu q, nu r are the beat frequencies measured at the location p, q and r respectively. The speed of sound in air is 330 meter per second. So which of the following statement is or true regarding the sound heard by the person? So here the key is to find out the beat frequencies at these different locations. So let us do it a little bit more clearly here. Let me draw the diagram clearly here. So these loudspeakers are situated at M and N, and the midpoint is Q here. Okay, this is the midpoint, and the cars is starting at the point P and ultimately reaches this point R. Okay, so first of all we have to find out the beat frequencies at the point P. So beat frequencies at the point P, to find it out, that is basically the frequency that is coming, frequency as measured at the point P coming from the loudspeaker at M, and it is the difference in the frequencies from the two loudspeakers, and we are measuring it at the point P. So this is what we have. This is what we have to work out to find out the beat frequency at the location P. Alright, so let us work it out. First of all, let us find out the frequency measured at point P, that is coming from the loudspeaker at M, at the point M. Okay, now if I sound is coming from the loudspeaker M in these directions towards this car here. Okay, this car is moving along this direction with velocity capital U, and let us say this angle is theta. So we have to now this is the case where the source is at rest. This is the source is at rest, but the observer is moving towards it. So first of all, the source frequency is this, observer is moving towards the source, so therefore the velocity of sound as measured by the person at the car would be simply small u, plus you have to take the component of this velocity u, capital U, along the direction of sound, sound velocity direction, so it would be capital U cos theta. And because the source is at rest, so it would be simply u here at the denominator. And so already we have done quite a bit of problem, so you understand it, that this is the formula I have to use. And similarly for the from the source, from the loudspeaker at N, the frequency measured at the point P here would be exactly the same formula, but the source frequency here is now nu n, and this is the same formula we have to use. So this is what we have to use. So if I combine these two things, then I can write this beat frequency at the point P as u plus capital U cos theta by u. I have nu m minus nu n, right? So this is what I will get. We can put the numerical value later on, but let us say this is the formula we got for the beat frequency at point P. So let me number it as equation number 1. Now what about bit frequency measured at the point capital Q, which is at the this is the point here at the middle of the bisector MN. All right, so this would be, because you see that here the sound velocity along this direction, but the source with respect to this would be at rest, right? This observer would be at rest, so I would have simply, this would be very easy. That would be frequency from the loudspeaker at M and frequency at loudspeaker N. So this is simple. So let us say this is my equation number 2. Now what about equation number what about bit frequency at the point R? Now in this case, this car is moving away from the source with velocity u. So therefore if I do this here, so this would angle would be again theta. So as it is moving away from the source, so obviously it is very straightforward, and you can clearly see that you will obtain this formula. I think it is easy to see that it would be u minus u cos theta by u, and then you have nu m minus nu n. So we have actually worked out the bit frequencies at all the locations. We have worked out it at all the locations. Okay, now as per the first option goes, it says nu p plus nu q, nu r, bit frequencies at point p and point r should be equal to twice that of the bit frequency at point q. So let us check it out whether that is correct. So if I add 1 and 3, so you will get nu p plus nu r, and this would be you will have nu m minus nu n. You can take it common, and then okay, just like let me just exclusively do it. Okay, it is u cos theta by u plus u minus capital U cos theta by small u. All right, so this would be simply twice that of nu m minus nu n, and quite clearly this would be twice that of nu at q, bit frequency at q. So therefore it is clear that the option A is correct one. Okay, what about option B, C and D? So option B says the rate of change in bit frequency is maximum when the car passes through Q. Okay, let us see whether that is correct or not. To do that, if you actually see these formulas 1, 2 and 3, you can write down a general formula for this bit frequency. So let me try that. Nu of t, you see you can write it as if you look at these formulas 1, 2 and 3, it would be nu u plus capital U cos theta. Now you see theta is this cos theta would be a function of t. Okay, I will explain that. Let me first write it. So it would be divided by u, and then you have nu m minus nu n. All right, as this car is moving towards this point Q, this angle theta is also getting changing. So suppose if this car reaches here, this angle theta is going to take a different value. Let us estimate that. First of all, let us see what this cos theta is. So as you can see that when it is at the point P, this total distance is say capital D here, and this small distance is say, this distance is okay, M and Q distance is say D. So therefore at that point the cos theta would be simply this base D divided by this distance, this hypotenuse. So you will have it as D divided by D square plus you will have this capital D square under root, but actually that is exact at the extreme point here, because this point, as this car is moving along this point capital Q, so I have to modify it. So therefore it should be like this, d, it would be d minus ut, because this distance would go on decreasing, right, as this distance, as it has gone through uh, from this point to this point. So at time t it will go by this distance, right? So therefore this distance that would be left out would be capital D minus ut. So accordingly I have to modify this formula. So you can actually easily see that you can write cos theta t as okay, let me write here, d minus ut square root of d square plus d minus ut whole square. So this is what you will get. So to find the rate of change of bit frequency, you have to find out the slope, right? D nu of t dt. So you just have to work it out. In fact, you can easily see from here, because it is cos theta. So this theta, in terms of theta also, maybe you can estimate it very quickly this way also. Say nu, because this guy is a function of theta, so I can write it d theta, then d theta dt. So here I will get, if I do it this way, then I will get it to be u, capital U minus u sine theta, and then theta, this would be time derivative of theta, then nu m minus nu n, but then there is a negative, so slope should be negative. Actually if you work it out rigorously by applying just putting this formula, so this expression that you should get would be for the slope d nu dt, you should be able to get it. You can do it, very straightforward calculation, but actually that is not needed here. The point is to see that the slope is negative. But anyway, let me write down the final expression. You are going to get the expression of this type. Okay, so we are going to analyze that. So d square divided by d square plus d minus ut 3 what is to the power 3 by 2. Now what you see that if you reach this point q, which is, if I at some time t, this total distance would be actually capital U into t. All right, so in that case this slope would be maximum, but it would be negative. So from here what I can conclude is that as the bit frequency starting from the point location p, the bit frequency will keep on decreasing, and it would become the slope would be has to be negative. And you see therefore rate of change of bit frequency is maximum when it reaches this point q. Okay, so from here if I observe this plot c, okay, first of all as regards the option B, the rate of change in bit frequency is maximum when the car passes through q, so this is correct. And out of this C and D, because the slope has to be negative and you see it has to be maximum at point q, so therefore the option C is the correct one. So therefore we can conclude that out of all these four options, option A, B and C are correct in this question. Okay, now let us work out this problem that was asked in 2013 JEE Advanced. Two vehicles, each moving with speed u on the same horizontal straight road, are approaching each other. Wind blows along the road with velocity w. One of these vehicles blows a whistle of frequency f1. An observer in the other vehicle hears the frequency of the whistle to be f2. The speed of sound in still air is v. The correct statement is or are. So you have to find out four statements are given. If the wind blows from the observer to the source, f2 greater than f1. If the wind blows from source to the observer, f2 greater than f1. and similarly in the other two options, f2 less than f1 and f2 less than f1. These are the cases, that is we have to find out what are the correct options. So in this problem, more than one option are correct, so let us find it out. Okay, so first of all, let us depict it pictorially, what is happening here. That say one vehicle, say A, and the other vehicle B, and both are approaching each other, moving with speed u. Okay, with speed u they are approaching each other on the same horizontal road. Now wind blows along the road with velocity w. Now wind direction is not actually given, so let us say all right, first say let us assume that the wind direction is along this direction, so along this B, and one of these vehicle blows a whistle at frequency f1. Let us say vehicle A blows at frequency f1, and observer in the other vehicle hears the frequency of the whistle to be f2. Say observer is B, so let us consider B as our observer and A as our source. Okay, so this is the situation here. Now let us find out the frequency as measured by observer B. So that would be f2, and then it would be with respect to source, that is your source frequency is f1. Now here the velocity of sound as measured by B, right? So this is what we have to find out, and then here it is actually the wavelength. So instead of f1, as per our formula, this would be the wavelength of sound as measured by B. Okay, so velocity of sound as measured by B. You see, if suppose wind velocity is along this direction from source to the observer, velocity of sound would be and first of all take the case where velocity of suppose there is no wind blowing is happening, so in that case you just write the velocity of sound as measured by B to be V minus u, right? V is the velocity of sound. V is the velocity of sound here. Small v is the velocity of sound. U is the speed or velocity of the observer. So therefore, because they are approaching each other, so this would be simply v minus u. Actually it is approaching, so it would be v plus u, right? Okay, if it is still. And on the other hand, if it is still, then you know that the wavelength would be, just recall that wavelength would be simply v, that is the speed of sound, minus speed of the source here. Source is also moving with speed u, velocity u, so into t0. T0 is the time period, so this is 1 by t0 is the frequency, that is nothing but your f1. So this is the case when we are having the still case, still air. Now when wind is moving, so suppose the wind is moving towards the observer, so therefore you just have to add v plus w, that is now the velocity of sound. Okay, because the wind is blowing along the same direction with respect to the wind, basically you are doing everything. This moving air is the medium with respect to which sound is basically measured, so it is be v plus w u, and this here would be v plus w minus u. So this is the formula when the source wind is blowing from source to observer. All right. Now let us consider the case where wind is blowing from observer to source, because these are the two cases that has to be considered in the problem. So in that case it will be simply F2 would be equal to F1 into wind velocity is now in the opposite, so it would be V minus W plus U, and you will have V minus W minus U. Generally speed is obviously always greater than the wind speed, so assuming that, and in from these two cases we see that if the wind is blowing from source to observer, then in this case it is easy to see that F2 is obviously greater than F1, and here also when the wind is blowing from observer to source, F2 has to be greater than F1. So it is very, you can quickly actually see it, because speed of sound is anyway V is greater than W wind speed. So this is what we are having. So in that case, if I go back to the options, so option A and option B are the correct one. Okay, so I think this is an important problem, and please think about it also. It's very easy. All right then.
So in this problem solving session today we solve problems on the topic Doppler effect. I hope you found this session useful. Thank you so much.